Hello, everybody. How you doing? Hope you guys are okay. We start in a couple minutes. So we are going to download Unit 4 assignment. I'll post the lab soon. I gotta edit a couple of things. Let me check if I shared the internship with you guys. Hold on. Oh yeah, I did. Okay. So I posted yesterday the internship for Riverside County. They have various internship. We talked to the sheriff department and I was just wondering if they hired computer forensic technician intern for their department. But if you like, you can check it out. It's in the announcement for Riverside County. It's between $11 to $18 an hour. So if you like, you can check the application. Okay. Okay, so if we can access Canvas and download the notes and the assignments for today, that will be Unit 4. Oh, I'm looking at the wrong folder. Any question before we start? Okay. All right. So I'm going to go into screen share. If you have any questions, please unmute and ask. Do you have a question, Isabel? I see Isabel on my screen. No question. Okay. So if you have any question, please unmute and ask. Okay. Let me zoom in real quick. I need. Okay, so in this week, we are going to cover part 1 of chapter 8. I decided to do 2 parts for this, for 2 parts for chapter 8 because it's require a little bit of understanding on combinatorics, and then we're going to go into permutation next week. Okay, so to start, to define combinatorics, it's a way that we would look at counting and finding the solutions by enumerating the solutions or finding the optimal solutions. So an example that you would see, which some of you have come across, if you go to like a restaurant, let's say that you want to order soup and sandwich and they give you many different type of soup and many type of sandwich. Or when you go to a fast food place and you can have different combo mix, right? So in the example on page 1, we see that Alice is ordering soup and sandwich. And there are 6 types of soup and 12 different sandwiches. So Alice must choose one of the soup or one of the 12 sandwiches. Now, when she selects the soup, she has to pick one out of the 6, or, right, the key word here is or, one of the 12 sandwiches. So in this case, what we use is we would use the sum rule. So when you have multiple options and you have to select one out of the multiple options, then you would have a sum rule. So I have a choice in 6 sandwiches and a choice in 12 soup, okay? So that will give me 18 different meals. So in this case, we would apply the sum rule. So if you have option A and option B and they are disjointed in a finite set. So last week we talked about what is disjointed and what is jointed, right? When we're looking at the Venn diagram, then we would have the number of ways by choosing a single element from A or B. So Alice has to choose one soup or one of the 12 sandwiches. So what we would have to use is the sum rule, okay? And the sum rule as it's defined on page 1 is that it would be applicable when one makes one choice from the union of 2 or more sets of alternatives. So in this case, we have soup and sandwiches. So we have 2 choices, the union of the 2 choices, but Alice has to make one out of the options, right? And the sum rule can be generalized in 2 sets of alternative as an obvious way. So when you make a decision out of when you have to select one or the other in 2 groups or 2 or more groups, then you would use a sum rule. So in the first question, it asks you, when is sum rule applicable? And we want to note that it is applicable when we make one choice from the union of 2 sets of alternatives. Okay. And so we can just simply state this. Okay, any question? So before we answer number 2, let's take a look at some more example. Okay, so you can find the answer for number 1 here on page 1. So as we see in example 2, right? Bob has to order both soup and sandwiches. So we can do a soup and a sandwich. There are 6 types of soup and 12 different sandwiches. Bob must choose one soup and one sandwich. So he has 6 ways to choose the soup and 12 ways to choose the sandwiches. So you can pair any soup and any sandwich, therefore we have to use the product law, okay? So that will be 6 times 12, which gives us 72 different variations in the meal that Bob can select. Okay, so he can do like a turkey and a garden sandwich, or the turkey soup and a turkey sandwich, and then, you know, different types. So what you have is you would have different variation in the meal with the product law. So in this case, you see that it is a little bit different than the last one in that we can choose one and another choice in the 2 sets, okay? So with the product rule, if A and B are finite sets, which is 6 and 12, and we have to choose an element from A and an element from B, then we would multiply the cardinality of A and the cardinality of B, okay? And we talk about cardinality is the size of that set, the number of elements in each set. So A has 6 and B has 12. So therefore, Bob has 6 times 12, which gives us 72 variation of meals. Okay, so let's take a look at our assignment. Any question about sum and product rule? So for quiz and test, you need to know the difference, right? When you use sum and when you use your product rule. So for number 2, it said at the movie theater, there are popcorn, candy, pretzel, nacho, and 5 types of soft drinks. You decide to select an item, that means an item of food, right? An item of snack, and a type of soft drink. So how many choice combinations do you have? So in this case, we have food and drink that we have to select. So that means that we would take 4 types of snacks times 5 types of soft drinks, which gives us 20 variation in our choices. Okay? So you can have popcorn and a Coke, right? Candy and a Sprite. So in many variations, as you can see, we can come out to have 20 different combination of choices. Okay, any question? So for number 2, for A, we would use the product rule. Now let's say that you only have money to buy one thing, right? Either something to eat or something to drink. Then you would have a sum rule apply, okay? So if we have to make a decision on either buying the food or buying the drink, then what we would have is we would use the sum rule. 4 types of snack plus 5 types of soft drinks, which gives us 9 choices. Okay, so that shows you the difference between the product rule and the sum rule in counting. Any question? Okay, no question. Okay, so for 2C, if you decide to select 2 different types of items to eat, 2 food items and a soft drink, how many choices do you have? So what we will see here is that we would start to look at when we select the first time that you make your choice, you have 4 options in the snacks, okay? After you pick one, so let's say I pick popcorn, then I have candy, pretzel, and nacho left, okay? Then I would buy a second snack item, so that means I have 3 options to choose from the second round. So that means I would take 4, that's the initial set to choose from. Once I select one item that left 3, so I would multiply it by 3, 4 times 3. That would take care of the snacks. And then we have to make one choice out of the soft drinks, the beverage. So we would take 4 times 3 times 5, because in this particular case, you're making you're selecting multiple times across the 2 sets, okay? So that gives you 60 different combination of choices. So for C, we would use the product rule because we have to select 2 types of food and a drink. Okay, any question? No question. Okay. So it asks you, when is the product rule applicable? So when we make 2 or more consecutive choices from the set of alternatives. Notice that in C, we made 1 choice from the 4 snacks that leave us 3 choice. So we reduce that by 1. So we multiply it by 3. That give us the snack, and then multiply it by 5 for the options for the drinks. Okay. So when we make 2 or more consecutive choices. Okay. In the sum rule, you would make 1 choice from the alternative sets. Any question? Okay. So before we get to the number 4, I want to take a look at a few more examples from the notes. And you can follow along, or you can preview the notes there. So in the text, it also provides some example that's, I took the example from the text and put it in the notes here. So you have personal identification numbers, PIN, which are entered into a numeric keypad. And so the pins that the people use is 4 digits. How many different pins are possible? So if we're looking at digits, we can go from 0 through 9, right? That would be our set. So that gives us the cardinality of 10. There are 10 numbers in that set, 10 elements in that set. Now, each pin would correspond with 1 element. So when I select the first number, it would represent the first D here. So let's say if I pick 0 here, right? And I select the second number, I can still keep it at 0 if I want. So in this case, we can repeat the number. So our cardinality is the same for every single digit, which is 0 through 9. So I can have 1, 1, 1, 1, or 0, 1, 0, 1, or many different variations. So we're trying to calculate out how many variations of 4-digit pins we'll have. So when you are able to repeat or reselect the numbers, right, or the cardinality stays the same in the set for every single digit, then you simply take the cardinality, which is 10, and you multiply it by, again, the cardinality, and then the cardinality again. So in this case, we would take 10 and we would apply it to the 4th power. We would raise to the 4th power, which gives us 10,000 different variation in pins. Okay, because I can have 4, 0, I can have 4, 1, I can repeatedly use the number for every digit. So that is why our cardinality stays the same compared to the last example. Once we select the item, right, if we cannot select the same item again, then we reduce it by 1. Okay. Like at the restaurant, they tell you to choose, an entree and a dessert, right? But you can only select that option entree once, right? And the dessert option once. So you would still use the product rule, but the second choice in the entree, if you select another entree, you cannot reuse that option, so you have to minus the 1. Any questions? So now if we have 7-digit pins, then we simply take the set size, which is our cardinality, 10, and we would raise it to the 7th power. So if we're looking at 7-digit pin, there's 10 million variation of PIN numbers we can derive from 0 through 9. Okay. Then on the next case, it asks us how many different 4 to 7-digit pins are there. So if we're looking at only a subset from that original set, if we have to select 4, 5, 6, 7 digits, right? Then we would use the product rule, and we have to separately count the sets. There's a 4-digit, which is 10 to the 4. There's the 5-digit, which is 10 to the 5th. There's a 6-digit, 10 to the 6th, and 10 to the 7 for 7-digit. So then you would have to add up all of these to give you the result. Okay. So if we have multiple sets of pins, 4, 5, 6, and 7 digits, then we apply the product rule and then we add them together. So you can have the union of these sets. Any question? Okay, let's look at the next example. So often that we would create programs that would have username and password, right? Or in some case, you might create a program to create password for user, right? Or, you know, it would generate some kind of passphrase automatically. So if we're looking at A through Z, uppercase, A through Z, lowercase, and 0 through 9, that we'll consider alphanumerics, okay? And in this case, we don't count all the symbols. We're just looking at uppercase, lowercase, A through Z, and 0 through 9. So for 8.2, question A, it asks, how many 4-character alphanumeric passwords are there can you use with upper and lowercase letters and digits? So we know that there are 26 uppercase letters, and then there are 26 lowercase letters, and then there are 10 digits, 0 through 9, right? That will give you 10. So for our set, you have to sum all of this up. You can't just say it's 26 or it's 10, right? It's 26 plus 26 plus 10, because we can select from this entire set. So when you take 26 plus 26 plus 10, that gives you the cardinality of 62. And if the user create the passwords from this set, then you would have, for 4-character passwords, then we would have 62 to the 4th power, which gives us a little bit over 14 million and a half. So 14,776,336. That will be our output. Okay. Any question? Okay. So let's look at case B. This should be a cracker. If a hacker has code that can try out passwords, right? Like it to brute force the system at the rate 1 password per second, how long would it take her to break into the system? So when we're looking at 4-digit passwords, right? We previously calculated that these are the number of variations for the alphanumeric passwords that are 4 characters. Then we know that if it is if it's 4-digit password, if it's numeric only 0 through 9, then we would have 10 to the 4th to calculate the variations of the password, which gives us 10 million. And if it's a second per password, that will be 10,000, and that will be 10,000 seconds, which comes out to be 2 hours, 46 minutes, and 40 seconds. Okay, so in a question like this, first you have to find out how many variations of passwords using a certain set. Once you have that, then you can convert that to the amount of time to crack each of the passwords. Okay, now going back to the previous question A, if we're trying to break 4-character case-sensitive alphanumeric passwords, then we would take the variations of those passwords, multiply it by 1 second, which gives us that many seconds. And if you convert that, that will be 171 days, 32 minutes, and 16 seconds. Now, realistically, the system is faster than that, right? 4 characters should be very short. It's not 1 second per password, okay? Like using, a software tool, I have tested, it's less than 27 seconds for 5-character password. So this is basically a slower system, a much slower system than what we have today. Okay? Any question? Okay, so let's take a look at your assignment. You have a combination padlock, and it requires that you use 3 numbers, like the locker, where you rotate left, you rotate right, and you rotate left again. So the number sets that's given to you is 0 to 40. And it asks you how many combinations of numbers do you use. So first, we need to determine our set size. 0 to 40, which gives us the cardinality of 41. Now, if we're not reusing the digit, right? If the requirement is that if they don't allow us to reuse the digit, then we would start with 41, which is the original set that we can select from. Then we pick one number that reduces to 40 for the second round. Then we pick a number and then it reduces to 39 for the third round. And since it's 3 numbers, we stop there, which gives you 63,960 variations in the combo. That's if we don't repeat the numbers. Now, if you're looking at if we reuse the number, we simply taking 41 to the third power, which gives us 68,921. Okay. Now, in realistic case, you would see that this is more of a valid answer because most of the time people would reselect that number, or they have the option to reselect that number in their padlock. But if the padlock requirement requires not to reuse the number, then that would be our answer. Okay. Do you have any question? Okay, no question? Okay, so let's take a look at number 5. An attacker is using brute force software to guess your password, which has 7 case-sensitive alphanumeric characters. A, how many different passwords must the software attempt? So we know that there are 26 uppercase letters, and then there are 26 lowercase letters, counting from A through Z. And then there are 10 digits, 0 through 9. So your cardinality or your set size is 62. We saw that in the example. Now we simply take that 62 and we raise it to the 7th power because there are 7 characters for the password. Okay. So that will be our output. Any question with 5A? No question. Okay. Now let's say that you decide to use symbols and there are 16 allowed symbols that you want to use for your password. How many attempts will the software try to guess your 8-character alphanumeric password with symbols? Okay. So at this point, what we want to do is we have to determine our cardinality with the symbol. So we take 26 uppercase letter, 26 lowercase letters, 16 digits, and 16 symbol, and we add it together, which gives us let me move it down so you can see. Which gives us 78. Then we would take that 78 and we would raise it to the 8th power because there are 8 characters for the password. And we would have the answer. So you can simply use your calculator, right? And you can put it into the scientific mode, choose scientific. So you take 78, here's the exponent option here, raise it to the 8th power, and that will be your answer. Okay, any question? So you will see questions like this for quiz and tests. Something similar to this. So as you can see, when we add the symbol, it creates a bigger pool of passwords. So this is why when, and also we raise it by 1 character. We increase it by 1 character. So as you can see, when you have allowable symbols to be added to the option for your set, it changes the scale of the password. Now in security, we say that we're just buying time, right? Time is a factor. So eventually somebody will be able to crack that password if they have the appropriate resources, which is processing power and time. Okay. So compare this to 7-character, you can see that it drastically is, and also we added the symbol, it drastically is larger. So this is why they require you to have at least 8-character upper, lowercase, numbers. and symbol. Okay, any question with B for number 5? Okay, so for C, we have to convert this to time and see how long that would take. So how long will the brute force software take to guess the password from 5B if the system takes 0.5 seconds to enumerate the password? So if we have this many passwords, that means that it would have this many attempts, and we simply multiply it by 0.5 seconds, which is half of a second, which gives you this many seconds. And then you can take that and you can convert it to minutes, hours, and then days, and then year. Okay. So we can see that with the 8-character password, alphanumeric, and symbol, it takes quite a bit of a long time if it's taking 0.5 seconds to guess each password. Now, of course, in reality, the system is faster, but it's still going to take time. Compared to 7-character password, it's drastically longer. Any questions? So as we go through, you can also take a look at some example in the notes as well, but you know, we use a lot of the exercise questions to really explain the concept. So let's look at example 8.4 on page 3 of your notes. So there are 3 sections of the class, like CIS7. One section contains 73 students. Another contains 64 students, and the third contains 61 students. Now, pay attention to how the question is asking. So whenever you see the word distinct ways is when you have to apply the sum rule and looking at the permutation. So it asks you how many distinct ways are there of choosing one discrete structured student to write up a sheet of notes for everyone to use on the final exam. Now, you know that in reality, when we pick that one person, right, that person is eliminated from the group, okay, and so forth. So we would first looking at the sum rule, because we have 3 classes. We have 73, 64, and 41 students combined. So first we add these together to look at the possibility. There's 178 students to pick from. Now for B, it asks you how many distinct ways are there to choose one student per class to be in the committee. So when we do this, we would use the product rule 73, 61, and 41, which gives us 191,552 variations of selection student. Okay. On the next one, it asks you how many distinct ways are there to list 6 different students from the third section, the 41 student class, to select them to go on the board one after the other to present the solutions. Okay. So we know that we start with the 41 student, we pick one, that person goes on the board, write it up, the solution. Then we pick another student with the 40 student that's left. That second person went up, write the solution. Then we have to pick one more from the 39, then one more from 38, one more from 37, and 36, and we would stop. That would give us 6 selection in the class. So you start with the original set cardinality, you remove 1, multiply it by that value, remove 1, multiply it by that value, remove 1, multiply it by that value, and so forth. And you would end whatever the number of the selection is, which is 6. And this is what we have. Okay? So what you see here is this is an example of permutation. And we would also expand on this again next week. But this is the basic at the beginning by just looking at counting. Now for the next one, we were asked to choose 6 students to form a volleyball team. Remember that there are 3 classes, so we started with 178 total from the 3 classes. We picked 1 student from the 3 classes. That gives us 178 here. That's the first pick. Then we're left with 177, and we're going to pick 1 more. And then we're left with 176, and we're going to pick 1 more. And then 175, select 1 more student, and so forth. And we would stop at 173 because that would give us 6 students for the team. So when you calculate this out, what this will be is that you would have each set of 6 student appears. That would be factorial 6. Okay, 6 factorial is going to give you 6, 5, 4, 3, 2, 1 times. So the number of set is the 6 students out of the 178. Okay. Any question? So when we make a choice and we have to remove that from the set, then we have to make the next choice from the rest of the options in the set, the rest of the value in the set, and so forth. So that would gives us what would we see in permutation. Now, 8.5, kind of like what we've been doing with the passwords, that's more of the combinations. Okay, which is different because you can have the same letter typed twice or 3 times or 4 times. So you can repeat the letter or the numbers as you create passwords. Okay, so if we have 6 case-sensitive alphanumeric characters, and we would have to have at least 1 digit and at least 1 letter. So we have to calculate how many there are. So first off, we know that the cardinality is 62 because it's alphanumeric, uppercase, lowercase, and digits. And there are 6 characters, so we have 62 to the 6th power variations of passwords, okay, with no restrictions. Okay. Now, if we're looking at letters only, then our size would be 52. Why is it 52? 26 for the uppercase and 26 for the lowercase, which give us 52. So you take 52 to the 6th power, which gives you letters only. Now, if we're looking at digits only, then 0 through 9 is 10 elements. So 10 to the 6th would be digits only. So what do we need to do after this? Once we determine the total number of passwords that we can have with no restrictions, passwords with letters only, and passwords with digits only, then what we can do is we can take the value that would be password with no restriction, we subtract the number of password with just letters, and we subtract the password with only digits. That will give us the difference. Okay. So that will be 1 digit and 1 letter. Now, if we expand this and we say if it's going to be 6 to 10 characters, and it must contain 1 digit and 1 letter, then we would have to do the set of 6, the set of 7, the set of 8, the set of 9, and the set of 10 combined. Okay, so you would find the value for only 6 with 1 digit, 1 letter, and then 7 character, 8 character, 9 character, and 10 character. So if we go all the way through 12, then you add 11 and 12, and that will be your result. Okay, any question? So going back here to our assignment, for 5D, it says, suppose the password have 8 case-sensitive alphanumeric characters that must contain 1 digit and 1 letter. How many are there? So first, we know that there are 26 in our set. 62, 26 uppercase, 26 lowercase, and 10, 0 through 9 for the digits. That gives us 62. We raise it to the 8th power. That will be passwords with no restrictions. Then we would have 52 to the 8th power, which just composed of letters only. 26 plus 26 gives you 52. Then raise it to the 8th power. Then we would have 10 to the 8 that are digits only. So we would have 62 to the 8th power minus 52 to the 8th power minus 10 to the 8th power. And here is your result. Question? No question. Okay. So you would find 5D similar to the example 8.5, or at least one part of 8.5. And in this case, what we will refer to is this is combination, but we use inclusion-exclusion principle, right? We include the entire set of the password. We exclude, right, the one digit and the one letter. Again, you will find something similar to this on quiz and test. So as you go through and review for your quiz or your test, you need to look back into your assignments, make sure you understand how to calculate these. Okay, so let's work on number 6. There are 3 groups of audience, 30 people in group 1, 40 people in group 2, and 50 people in group 3. How many distinct ways can a person be selected from all 3 groups to win a prize? So we would do a sum rule here. We would take group 1, which is 30 people. We would add it with group 2, 40 people. And we would add it to group 3, 50 people, which gives us a total of 120. If we pick one person, that will be out of that, the 3 groups, we would have 120 ways to pick one person out of the group of audience. 3 groups of audience. Now for 6B, it asks you how many distinct ways can a person be selected from each group to meet the performer. So here we would use the product rule. We would take 30 from group 1 times 40 from group 2 times 50 from group 3. So we have 60,000 ways to pick one person to meet the performer. Okay, very much like the discrete structure class example 8.4 that we covered. Then for 6C, it asks you how many distinct ways can 5 people be selected from group 3 to win tickets for the next event. So you would take group 3, which is 50 people. You would start with 50 for the first selection of that person, and then remove that person, we would have 49 left in that group. Pick one, 48 left, pick one, 47 left, pick one more, 46 left. And here we have 5 selection of 5 different people. So we would multiply these together, which gives us 254,251,200. variations in selecting or distinct ways to select 5 people from group 3. So the last part of 6, question D asks you to find the distinct ways for 5 people to be selected from all groups to win backstage passes. So remember that we started with 120 for all 3 groups. So again, we would take 120 times 119 once we pick one person, times 118, pick one more, times 117, pick one more, times 116, and that will be the result. Okay, any question? So as you see in every chapter, you see that for us, we have to look at how we can logically solve these problems. And when you're looking at from a programming perspective, you have to see how you can implement logic in your program to be able to have the appropriate output. Okay, so for inclusion-exclusion principle. So we talked about the sum rule that you must make one single choice out of the set of alternatives, and they are mutually disjointed. They're separate sets, okay? They do not share common elements. Now, the single choice must be made from the set of alternatives which are not disjointed in such that we would have them be combined, okay? So as we look at this last week, when we go over the diagram, we talked about the intersection. So you would see that here is the population for A and the population for B. And if it's not disjointed, that will be an intersection. So you have to take a look at how these two are combined and subtract this white area to get the red area, that small intersection. So we would apply the inclusion-exclusion principle. So you would simply take A population plus B population minus the intersection of A, B. Okay, so let's take a look at 8.6 so you can see more how this would apply to counting. So it asks you how many strings of 6 uppercase letters start with A and end with Z. We know that there's 26 characters in the alphabet. And we would have 26 to the 5th power that would start with A. Why is it not 6? Well, because you have A is a character, so you cannot include that. So you would have 26 to the 5th. And again, we would have 26 to the 5th and with Z. So if we say, okay, well, what if we wanted to start with A and end with Z, then we would have 26 to the 4th power starts with A and end with Z. Notice that the exponent is 2 less than what is asked here because you don't include A or Z as part of that exponent. Okay? But then you have to be counted twice. So technically, the easier way to do this is we start with everything, 26 to the 5th for A, 26 to the 5th for Z, add those together, then we would subtract 26 to the 4th that starts with A and ends with Z to give us the right answer using inclusion-exclusion principle. Okay. All right, let's look at 8.7. This is going to be similar to our assignment. It asks you how many positive integers between 1,000 and 9,999 inclusive. There are 9,000 consecutive integers. So you would take 9,999 minus 1,000 plus 1. So if it asks you how many positive integers between 1,000 and 9,999, then you simply take 9,999 minus 10,000 plus 1, okay, which gives you 9,000. So we're looking at this set here. This is the start, this is the end. And if we count up all the positive integers, that will give us 9,000. Now for question A, it asks you how many is divisible by 9? So you know that the 9th integer is divisible by 9, right? So we would have 9,000 divided by 9 evenly, which gives us 1,000. So every 9th digit would be divisible by 9. So the answer for that would be 1,000. For B, 8.7, it says, how many are even? So we started with 9,000 from the first part here. And if we wanted to make it to determine how many that are even, we would then, we know that half of the integers are even and the other half is not. So we would take 9,000 divided by 2, which gives us 4,500 that are even. Any question? For C, it asks about distinct digits. So The leftmost digit cannot be 0. Why is that? Because we start at 1,000. We start at the 1,000, right? It cannot be lower than that. So the leftmost digit cannot be 0. It has to be 1 or higher, right? So there are 9 choices. So when you're looking at 0 through 9, that's 10. And if you eliminate 0, you would then have 9 choices left. Then the second digit can be any digit but first, so there are 9 choices, okay? And then 8 choices for the third and 7 for the fourth and so forth, because they have to be distinct. I cannot have 1, 1, 1, 1, right? I have to have, 1, 2, 3, 4. I can have 1, 2, 3, 4, 5, but I cannot have all the same because they have to be distinct. So if you have it, you cannot have the 0 in the front because we start at 1,000. So that first one needs to be a 1 or higher. Then the second digit, it can be any digit, but it cannot be the 1 or like the previous one. So if the first one is 1, the second one has to be any other number, so it's 1 less. Okay, so that would also give you a 9. And then this will be 2 less because the first 2 already took the positions. So you would have only 8 out of the set left to have the distinct digits to select from. So that will be 8. And then when we select that digit, then we would have 7 that we can make indistinct. So that gives us 4,536 distinct digits. So this one is a permutation. Okay, any questions? Okay, so let's go answer number 7. So 7 asks you to use inclusion-exclusion principle to determine how many positive integers between 100 and 987 are inclusive. So we have the range that's given to us here, 100 to 987. So you take 987 minus 100 and then you add 1, which gives you 888. Then for A, it asks you how many positive integers between 100 and 987 that are divisible by 8. So we know that every 8th digit is divisible by 8. So we simply take 888 divided by 8, which gives us 111. So 111 positive integers between 100 and 987 are divisible by 8. Okay. Any question on number 7A? You can also refer to the example, it's similar. So for B and C, it asks you, for B, how many positive integers between 100 and 987 are even? Very much like the example, right? So you take 888, which you found at the beginning, and you divide it by 2 because half of that group is even and then the other half is odd. So you have 444 numbers that are even in that range. So for C, we have to determine the positive integers in that range that have distinct digits. And you notice here that we're working with 3 digits. 100 has 3 digits. 987 have 3 digits. So the leftmost digit cannot be 0 because it starts at 1. Cannot be lower than 100. So we have 9 choices there. The second digit can be any digit but the first, so you also have 9 choices. And then the third digit, it can be any number except for the first and the second, which gives you 8 choices. So here at this point, we would apply the product rule. We would take 9 times 8, and we will get the answer for C. You don't have to type it out like what I have. I just type it out as in also in the notes, so that way you can see how each step, how we go about looking at each of the steps so we can solve the problem. Any question? Okay. As we didn't finish the last few here for the example, if we're looking at going back to this, right, 9,000 from what we found in the example, if we're trying to see how many are not divisible by 3, then we know that every third integer is divisible by 3. And if you take 9,000 divided by 3, you get 3,000 that are divisible by 3. So you have to find the difference at that point because it's asking for not divisible by 3. So you take the 9,000, subtract 3,000, which gives you 6,000 that are not divisible by 3. Okay. And we can do the same with 5 or 7. So you simply look at how you can determine divisible by 5. So every fifth, right? Plus the number that's divisible by 7 minus the both. Okay. It would be like this. So you will get various part of final exam questions that would include inclusion-exclusion principle from counting, and also we would reapply this in the next couple of chapters, so you will see it again, right? And that started with last chapter when we talk about sets. So this example can expand a lot further, as you can see, divisible by 4, 8, 12. So we have to take a look at the criteria that they're asking for and be able to determine, right, what to be include or exclude from that population. Any question regarding inclusion-exclusion principle? Next, we're going to talk about Pigeonhole Principle. So based on your notes here, it tells you that Pigeonhole Principle states that if you have k plus 1 or more objects that's placed in a k box, there must exist a box that contains 2 or more objects. Okay, so let's say that I have 12 cages for the pigeons, and then there are 13 pigeons around the area. And as the pigeon enter each of the hole, right, you would have the extra one that would enter into one that already have a pigeon inside. So you would have 2 or more, okay? So the example here is that if there are 13 people gather in the room, it's guaranteed that there's at least 2 of them that share the same birth month. At least 2, okay? Because why? How do we know that? Because there are 12 months in the year. So while if you have 11 people in the room, there's no guarantee that you would have 2 or more people that would have the same birth month based on Pigeonhole Principle. Okay? So let's look at example 8.8. There are 102 students in 2 classes, 2 sections of the class. If they all take the final and at least 2 of them get this, will 2 of them get the same grade? So we have to take a look at the possibility of the grades, okay? There are 101 possible grades because you can have 0 through 100, which gives you the set of cardinality set is 101. Somebody can get a 0, somebody can get 100, somebody can get 99, right? So you have 101 possible grades. Okay. Now, if you have 102 students, can they have the same grade? What do you think? This is more than our grade option here, right? So yes, likely that you will have at least two or more students that have the same grade. For 8.9, it says if they list grade, which they can't do that anymore. They used to do this. Okay. If they list they use the 2 digits of the Social Security or student ID and they post the grade. Okay. So you would have 100 of the 2-digit codes, 00 through 99. That will give you the cardinality of the digit codes. And if you need to list 101 students, so that way you won't have students that would have the same code. Okay. Any question with Pigeonhole Principle? So we'll expand a little bit more on this next time, right? We'll expand a little bit more in chapter 8, where we kind of dive into more examples and take a look at how we can calculate this. But so this is just the beginning using product and sum rule. So in example 810, it says that in a drawer you have 12 red socks and 12 blue socks. And if you need to remove the socks in the dark from the drawer, right, will you get a match? So how many times do you have to take out in order to get the matching socks? Okay, well, the answer here is 3 because there are 2 colors. So you have to pull at least 3 socks from the drawer to get a matching color, because a pair is 2 socks based on Pigeonhole. Okay. Now, if I only want red socks, how many times do I have to take the socks from the drawer to get a matching pair of red socks, right? And recall that we have 12 blue and 12 red. So we would have to have 14, okay, because you might have pulled all blue ones, which is 12. You take, let's say you just pull them and you would get 12 blue ones, and then you have to take at least 2 more to get red socks. Okay, so if we eliminate all the blue from the drawer by taking all of them out, then we would have 2 more to get the red. Okay, because there are only 12 blue socks and 12 red socks. Now for C, it says, how many do you have to pull to make sure that at least one of each color? Well, you have to do 13 because you might get 12 of the blue and then the 13th one would be the red. Okay? Any question? So here it shows you some explanation what mod and what proof. Will come back to showing how mod is applied to this in the next, after near the end of this chapter or going into the next couple of chapters, so you can see, because it will come a little bit clearer when you start, we're going to start going into polynomials and things like that. But in general sense, when you have a collection of number, you have to have at least that amount or higher to really fulfill the pigeonhole principle in the selection. Okay, as large as the average. Okay, so let's touch on the last question, and you're gonna have an early night tonight. Actually, the last 3, which is short. If there are 38 people in the room, how many people would be guaranteed to have the same birthday, the same day of birth? So when I'm talking about the day of birth, meaning like the 1st, the 2nd, the 10th, the 14th of the month, okay? It doesn't necessarily match, doesn't have to really match with the birthday with the birth month. Okay, so we're just talking about the day. So let's say that you have 38 people and you ask, what day were you born, right, in the month? And they would say the 10th, right? So will you have 2 or more people that would have the same day? The answer would be yes, because you have 38 and the maximum number of days in a month is 31 days. Okay, so you would have 2 or more people that would have guaranteed the same day of the month for their birthday. Now, if you have 18 people in the room, that's not guaranteed, right? Based on Pigeonhole Principle. Even if you have 28 people in the room, that's not guaranteed either, because if you're looking at leap year or February, right, then that will be 28. But when you're looking at leap year, that's 29 days for February. And then you have some months that will have 30 days and some months that will have 31 days. So as long as you have more than 31, then you would have a guarantee of the same day in the month. Any question? So for permutation, permutation is an ordered arrangement of set or the subset of objects. Now in C++, C++ library, if you use algorithm, right, you would see that there is a function, multiple functions that's used for permutation. And what it does is it compares, it creates variations of the output from the given values as elements based on the previous, the first, or the last. Okay, so we'll touch a little bit on that, on permutation this week. It's a little bit harder concept to grasp. You have to understand how text is seen by the computer and how it interprets it as value and calculate it as value to really see how it does the comparison from one to the next. Okay, so we'll explain that on Wednesday. And I will have the lab posted, for Thursday. I apologize. So here, Dr. Fowl give you a little bit more explanations, and she gives you the example of errands when you choose to run an errand, right? And then you would eliminate it from that choice. And then the next errand, you would eliminate it from that choice. So the formula for this, for the distinction in the elements, is that it would be the factorial of n. Okay. So let's say that if you have 8 in that set, right, and you have to permutate through the values for the values of those 8 elements, that will be 8 factorial. Okay, because in here, technically it's n times n minus 1 times n minus 2. We would reduce 1 as we go down the list. So that we would have the proper arrangement in the variations. Remember, the permutation order does matter. So what do I mean by that? Things like this. 1, 2, 3, 4, it's different than 1, 3, 2, 4. Okay? And it's different than, so what you see is that when it permutate, we have these values, once that's selected, right, it will be distinct from the other one because the order does matter. The 2 goes before the 3 does matter compared to the 3 goes before the 2. Okay. Question. So I'm going to finish with this part because we will pick it up next week starting from here with this formula. Okay. So in counting permutations, the way that we write it is that here is our set, right? And here is the choice, R. So let's say that you have to make 2 choices out of the 6 options, then your R is 2 and 6 is your N value. Okay. So that way that you can apply into the formula and calculate. Now, if we look at example 14, so you can see at a wedding party, right, we want to choose to arrange people so that way that they can take pictures in a row. Okay, and there are 12 people at the wedding party. So your set here is 12. So the way that we would arrange them in variations is factorial of 12, right? 12 times 11 times 10. And as you notice, factorial, we reduce one each time that we move to the next. Because when we choose people, right, we pick one, we put them in front of the camera, the next one, so we would reduce from that group one each time. So you have 12 times 11 times 10 times 9 and so forth until we get to the end, which gives us 12 factorial. Okay, so that will be the number of ways that we can arrange people. Now, if we wanted to choose 2 ways to arrange, right, the bride on one side and the groom on the other side, then you would have, so it asks you here, it says, how many ways does the bride and groom stand together on the left side of the line? Okay. So there are 2 ways to arrange the bride and the groom on the left side. Line 1, you would have 10 and 10, so 10 factorial, because why? We remove the bride and the groom, and then you have the 10 people surrounding them. So that would be factorial of 10. Now, that is only half, right? So what we have is we have 2 ways of that. So we have to take that and we multiply it by 2, because you can have the bride one side and the groom on the other side, and then you switch it. Okay, so you have to multiply it by 2. And then for C, it tells you how many ways if the bride and groom are together, but anywhere in the line. So you originally have 10 factorial ways to arrange the guests without the bride and the groom. Now, if you add the groom, so it says if the bride and the groom are together, then placed between the 2 of the lineup people, left or right of them, you would have 11 different positions. So you would take factorial of 10 times 11 times 2. Okay, this is a little harder because that they threw in the criteria that they could be anywhere in the with the people that's lined up. So that would have the 1 added, but because you have bride and groom, so you have to multiply that by 2. And if you have 5 people taking pictures, then you would choose 5. So here, what we're doing is we're choosing 5 out of the 12. So your R is 5 and your N is 12. So earlier we saw that we did this 12 times 11 times 10 times 9 times 8. We stop at 8 because that gives us 5, right? Another way that we can do this is to use the formula that's given here. So we can say that we can do 12 factorial, right, is divided by 12 factorial minus, or 12 minus 5 factorial. So 12 minus 5 factorial. And that would give us also the distinct ways to pick 5 people for the picture. Okay, any question? So we'll go a little bit more with the formula and with the exercises. Next week we'll do a few more exercises with that. And here 8:15 talks about different places to visit with the possibility, with the iterations. So you can follow that to look at that example if you wish. So make sure that we know the definition for permutation. It's an ordered arrangement in the set or the subset of objects. Okay, so let's do the last one. Let's say that we have Netflix. Now they just do subscription for, right? So when I wrote this question, I had no idea of what Netflix consists of. So forgive me if I'm way off. But think of I probably meant like Redbox or something here. That would make more sense. But okay. Let's assume that you received 10 free movies from Netflix, 5 comedy, 2 action, and 3 drama. If you only have time to watch 3 comedy movies of the 5 free option, how many, sorry, I have a grammatical error, how many possible arrangements of comedy movies can you watch? So we know that we have 5 comedy movies. So 5 times 4 times 3, and we can only watch 3, right? So you take 5, you watch 1 movie, so you remove that one from the list. Then you have 4 left, watch 1 more movie, remove that from the list. Then you have 3 left, and then watch 1 more. That would give you 3 options. So 3 selections. So you would have 60 variation in watching 3 comedy movies of the 5. Any question with 10? Sorry about the crazy highlight. I wanted to show the differences here. So on your day off, you decide to watch 4 of the free comedy movies, 2 action movies, and 3 drama movies. How many possible combination of movies can you watch? So you start with the comedy, which is highlighted in yellow. So 5 times 4 times 3 times 2. And you can apply the choosing formula here too. Like your R is 4 and your N is 5, right? And then you gotta combine that with the other one. But I choose to do the product rule here so you can see. 5, 4, 3, 2, multiply to get the comedy. Since we have only 2 action movies and we're watching both of them, so you just multiply by 2. And then we have 3 drama movies and we're watching all 3 of them, right? Then you have 3 times 2 times 1 for the drama. So when you multiply everything together, you should get 1440. Okay, so that's distinct ways of watching your comedy, action, and drama movies. After this class, you're going to see things very differently, from casino to, you know, when you go to a restaurant, when they give you all of these options to order, when you have to pick a choice, you're going to start calculating in your head. You're going to say, oh, I have this many choices. Or when you buy lottery tickets, right? If you ever sit there and you can calculate your possibility of winning lottery tickets. Okay. Any question? Okay. Last, see if you decide to watch all the comedy movies. First, A, B, C, D, E, then watch action movie. Remember, this is order matter, right? we watch them by a specific order, how many distinct arrangements are possible? So factorial of 5 times factorial of 3. Where did I get the 5? From the comedy. And then I multiply it by factorial of 2, which is 2. And so that would give me 240. Any questions? So as a programmer, we got to start thinking about, like the type of data that we're working with and how we're able to solve the problem using the values in that data set. Okay. In the case where if you see like combinations and options like this, it's very common for business use. Okay. Like for example, if you see like Pizza Hut, Domino, fast food restaurants, you see the options that are presented. So when you write those type of interface for people to select, you have to have an expectation of what they would be picking. And behind the scene is that business still have to calculate out the possibility to see if they're actually profiting still by giving these options. Okay, that's a little bit on the data analysis side. So any questions? Okay, so we finished about 20 minutes early today. If you have questions, you can stick around. I'll take some time to go through and answer questions with you. If not, have a wonderful night, and I'll see you here on Thursday. We'll do some programming in C++ with permutation. Put your name in the chat if you wish, but I pulled the participant list. So type your name in there if you're using a nickname for Zoom. Okay, enjoy your night, everyone.
Good night. Thank you.
You're welcome. Any questions?
So are the assignments a good reference to what the quizzes and exams would look like?
Yes. Quiz and exam are multiple choice. Quizzes, you can use notes, and it's like 3 attempts. So best score out of 3, you'll get, you get the highest score recorded. I forgot to mention the extra credit. I'll mention it again on Thursday, but there's a quiz review game that's posted. I use quizzes, which a lot of like teachers from grade school use, but it's a fun little game. And if you participate and you take your screenshot of your score, you can get extra credit by just submitting the screenshot of your score. The person that has the highest score, I send an e-gift card. So I do it for all my class every semester. So if you do it, you might have a chance to get the high score. And it's a preview of your quiz, what it would look like. So it's like a pre-test. Okay. Any other questions? Thank you, Albert. Have a good night.
Oh, hi, Professor.
Yes.
For number 10, the section B, why is now there's only three drums movie? Why now 3 instead of 3 times 2 times 1?
It is for 10B.
Yes.
It is 3 times 2 times 1.
Because you're going to get 3 drums movies. There's no other options to choose the drama movies.
So for the drama movies,
Mm-hmm.
10B, it says, okay, so you watch 4 comedy movies, 2 action movies, and 3 drama movie. So your question is, why is it not just multiplying by 3?
Yes.
So technically, you watch one after the other.
Mm-hmm.
You cannot watch 2 or 3 simultaneously. So you watch one, so I can do like a free comedy with the one action with the drama
Mm-hmm.
in variation. So you still have to permutate with that. They are grouped together as they would go together, like you would do comedy, action, and drama. So as you look at the 3, you watch one and you eliminate that, and then you have to pick from the 2. You still have to make a selection from that subset. So you have to multiply 3 times 2 times 1, because
Okay.
you cannot watch all 3. So if you multiply it by 3 by itself, that means that you're watching 3 at once. Like you turn on three of the comedy movies and watch it once. And realistically, we cannot do that, right? We watch one movie, and then so that option is eliminated. Then you have the 2 left. Then option that is eliminated, you have the 1 left, because you would mix them with the action and the comedy. That is why we would have to do 3 times 2 times 1. Let me go back to the share screen so I can show you.
Because I just feel a little confused about like the question asked about like we watch all three drums movies and there's only 3 drums movies we have. So
Right.
yeah.
But I think that the intention for the question is you would do a comedy and then an action and a drama, right?
Mm-hmm.
With as a combination. So as you go through and make the choices from the 3 movies, since you only have 3, you still have to pick one drama from the 3. You see?
Okay.
Yeah, you still have to make that choice from the 3. Yeah, the question was not very clear, but it's intended to be a permutation where, once you watch that movie, it's eliminated, right? Because they only give you that one free. So that order does really matter, because I can have A, B, C is different than B, C, A, right? And
Okay,
so
yeah.
forth.
Okay, thank you.
You're welcome. Any questions, Michelle or Alexis? You have any questions? You okay?